Good morning, my name is Patrick Vince and I am the leader for Experiment 4, which is the vapor compression refrigeration heat pump. The experimental objective for this experiment is to learn how to measure the coefficient of performance, which is basically the efficiency of a refrigeration cycle, and to describe the vapor compression refrigeration cycle in a pH diagram. And we will be doing two different tests to hopefully accomplish this. Test 1 will be to determine the inlet power, heat produced, and then the coefficient of performance. And then test 2 will be to lay out the compression cycle in a pH diagram and then compare it with the ideal cycle. So this is a diagram of the Edibon TRCV rig, also known as the computer-controlled vapor compression refrigeration unit. This is what we're going to be using in the lab, and as you can see, there are many components to it. So I tried to highlight the four main components in yellow, and you'll see there's a compressor, a condenser, and then an expansion valve, and then an evaporator. Those are the four main components in the vapor compression refrigeration cycle. So those are the important ones, and everything else are basically just sensors and pumps and things of that such, and I won't bore you with all their little titles. So real quick, an ideal cycle versus a real cycle. As we all know, ideal cycles are reversible, and they don't change the system or the environment or anything like that. And real cycles are not reversible, and things that kind of render a cycle irreversible is friction, expansion, heat loss, all the things we learned in thermo. So the lab manual said to try to explain what a thermostatic expansion valve was, and I'll be honest, I didn't know this existed until I started researching it. So this is my very crude explanation. But basically, the thermostatic expansion valve, it serves one purpose and one purpose only, and it's to regulate the rate at which liquid refrigerant flows into the evaporator. And it does this by matching the flow rate against how quickly the refrigerant basically evaporates off the evaporator coils. And like I said, I'm not sure, but it basically measures the temperature and the pressure inside of the evaporator, and then it uses, there's like a spring valve here, and it does some magic inside there, and it regulates the flow of the liquid refrigerant into the evaporator. I'm assuming there's probably one somewhere in that diagram we saw earlier. Just because here's figure 1 shows the refrigeration cycle, and then it shows, the evaporator, the compressor, and it's all the yellow highlighted components earlier, and then the TS, pH, all these diagrams we've seen 100 times, and the processes, which I'm not going to bore you with. They're readily available in the book and the internet. If you're interested, feel free to go look them up. So for the first part of this experiment, there's two tests. They're both very similar. This is the first one, and procedure is pretty simple. We're going to start the software. We're going to turn on the two pumps to get the evaporator condenser operating, and then we'll set the flow rates to 5 liters per minute, and we'll set the compressor, and then I guess we're going to let it run until it becomes stable, and then we're going to record some data in this table, and the recorder will use that to calculate the electric power to produce heat and the coefficient of performance. This is for the first test. And the second test is very similar, except we're going to do it for 3 different cases, and for each case we will adjust the evaporator flow rate from 3 to 4.5 to 6, I guess, to get a few different results. let it run until it becomes stable, and then record a few more values. And I guess they're going to use these values to come up with a pH diagram. I didn't read that far. There's a lot of stuff in that manual. A couple things to remember. On the pH diagram, P2 equals P3 and then H3 equals H4, so that will probably be helpful at some point. I did a little sample calculation basically to show the equation for the COP, and it's just the desired output over the required input, and then all that other good stuff there. But I assumed MOV00A as a working fluid, which is what we're going to use in our experiment, made up a temperature and a pressure, and use the tables and do all that fun math stuff and came up with a COP of 3.41. I don't know. I mean, it said that COP can definitely be over 1, so I'm assuming that might be something close to what we get in the lab. There's some references. Any questions?